this. Right. Right. If you remember the issue of whether the discrete time signal was periodic or not had to do with whether you can find a number of samples after which the signal repeated itself. So in the case of the first question is cosine 0.125 pi n, which is pi n over 8. So if I can find a whole number, an integer, where this particular, let's get a little pen here, where the original signal, and if I go n samples down the road, the values are the same, then that will be the period of the signal. If I can't find an integer value where that happens, then the signal is not periodic, regardless of how the envelope looks. And we made a distinction about that the thing, your eye could tell you that, yeah, there's a sinusoid or a cosinusoid signal. But from a discrete signal point of view, if the values are not identically repeating, then it isn't periodic, all right? So if you look at this thing, what I'm saying is that cosine pi n over 8 or 0.125 pi n, right? I am supposed to find, if I change n to n plus some number, then for this to be true, it means that this is only true if n pi over 8 is a multiple of 2 pi, right? Because we know cosine or sine repeats itself after a period of 2 pi radians. And this is only this will only be true if n, in this case, for n equal to 16. So in this particular instance, after 16 samples, that particular signal will repeat itself. So it is periodic, and the period is 16. Notice that the period is twice this number here, right? Fair enough? Yeah, no, maybe. Right? The second one, there were two signals, a cosine n pi over 12 and a sine n pi over 18. Right, so the only way this can be periodic, first off, we know that the n pi over 12 from the first part, n pi over 12 will be periodic with a period of 24. And n pi over 18 is going to be periodic with a period of 36. So if we add the two of them together, what we need now, the only way that will happen is if there's some integer that is a multiple of 24 and 36. And if you remember back from primary school, something called LCM, lowest common multiple, right? So what you need is, what is the lowest common number that both 36 and 24 will go into? And the lowest number that both of them will go into is 72. So in other words, after 72 samples, the joint signal comprising of the cosine n pi over 12 and the sine n pi over 18 will repeat itself entirely. The actual values will repeat itself. Your mind may telling you in between that, if you look at it, you may well see something looking like this kind of thing, right? Where you're seeing values that might be looking like the envelope might be repeating, but the actual value is not, right? After 72, however, this one will actually go and repeat, okay? The next one we have here is sine pi plus 0.2n. Now this one, if you try to find it out, The only way this can work is if 0.2n is again a multiple of 2 pi, because sine repeats itself every 2 pi radians. That can only happen if n is a multiple of 10, well, if n is equal to 10 pi. But we know that pi never repeats itself. So there's no way that I can get a value of n that will make 10 pi an integer, because pi is an irrational number. It doesn't repeat itself. It's gone up to, I forget how much, hundreds and hundreds of millions of decimal points, and it's still not repeating itself. All right. So something like sine pi plus 0.2n from a discrete signal point of view will not repeat itself. If you plot it, however, the values, right, the envelope will look quite sinusoidal to your eyes, but from a signal processing point of view, they are not. Okay. This one, e to the j pi n over 16 plus cosine n pi over 17. Remember, e to the j, whatever, e to the j theta, this is cosine, oops, doesn't write good on a PDF anyway. Okay, whatever. This is, I had a white screen for this anyway. This bit here is cosine plus j sine. So this is really cosine pi n over 16 plus j sine pi n over 16, right? And remember, the j is just a phase angle, right? So it's a cosine plus a sine that is off by 90 degrees plus another cosine. So the cosine part of this will repeat after 32 samples from what we did before. The sine part of this will also repeat after 32 samples. And the cosine part here will repeat after 34 samples. So if I have the two of them together, the only signal, again, we're going back to the LCM, we need something that is common to both 32 and 34. So the nearest value n, or the lowest value of n that we're going to get, is going to be 544. So after 544 samples, right, that signal above their xn, the sequence of values is going to repeat itself. So that is periodic with a period of 544 samples. Okay, what is the frequency of that signal? Well, that depended on what was the interval between the samples. Right, we didn't have enough information to say that, but if 544 samples and I'm sampling at 0.1 second per sample, then I know that the whole period will be 544 by 0.1, and therefore the frequency will be 1 over that. Yeah? Make sense? Anybody had a different slant on it? Anything? Anybody had a different look at it or anything like that? All right, good. Okay, so let's get to the next one here. So the next problem was, what is downsampling and upsampling? Well, that's straight from the notes. The downsampling and upsampling have to do with whether, when we downsample, what we do are to take the sequence of numbers that we have, and by downsampling, we remove samples at a particular interval. All right? When we upsample, we insert values in between the samples that exist. So that's straight from the notes. I had a little blank screen here. Right? So if you remember, if I had if I had a series of values, for example, if I downsample this, what I did to downsample is to make the number of samples less. So what I'm going to do, if I downsample by a particular factor, so like in this question, we're asking what is x3n. So if I downsample, if xn is this and x3n, what I'm doing is that every 3 minus 1 or 2 samples I'm getting rid of, and every third I'm picking. So I'll pick x3 and I'll pick out this one, discard this, pick out this one. All right. So downsampling, you discard values depending on what is said inside of here. Upsampling, you insert values depending on what is said in here. So x3n, if I'm upsampling, it means I'm going to insert 2 samples between each successive one. So if I had the original ones here, if I'm upsampling, then I'm going to put a value here and a value here, 2 samples, right? So between every 3, I insert 2 here, here, and so. All right. So they normally go together. We downsample because depending, as we said, depending on the nature of what you're dealing with, right? The amount of data that you have, you may have to reduce the amount of data that is stored. So if you know what you have and it is fairly consistent, then you could get rid of some of the intermediate samples and save a smaller file that is representative of the big one. And then when you want to reconstruct the file at the end, you upsample it. Okay, and there were a couple of examples that we spoke about in class. In one case, when you upsample, you could insert zeros in between the successive values, or you can sometimes use 2 values and connect them with a line and insert a value according to an equation between the 2 of them. All right. Question 3, again, was all about upsampling and downsampling. This was also to get you, if you wanted to try it, you didn't have to, but you could use MATLAB to sort of to obtain the plots of these things. So the first thing, this was a sequence here. Let me see if I could get the solution. You have the solution in your right, posted online. Let me just get the solution back here. So that's this. Right, so let me just go down. Right, so this was xn 6n into un minus 6. These are unit steps, right? So un, and the only reason, remember, we've gotten into the habit of, okay, I'm not going to do that. Sorry, that delete. Okay, right. So we've gotten into the habit of using square brackets inside of here. All right. So our normal thing would have been x square brackets and etc. etc. So this is the sequence here, right? Un is a unit step that is starting at 0 and going all the way 0, 1, 2, 3, etc. etc. all ones. Un minus 6 is the same unit step, but is starting at n equal to 6. So it's a delayed unit step. And the difference, of course, will just give you 6 values in between. And then I'm multiplying it, I'm scaling it by 6 minus n. So that's why I get these dots here. You can have some time and play with it. The rest of the things now have to do with what, how do I manipulate this? Now you can look at it from and this was the idea inside of here, to look at it from an upsampling or downsampling point of view. So if I go back to the whiteboard that I have, good. Right? So if I have, for instance, right, so I have a series of values here, right, coming, right, whatever it is, something like that. If I tell you now that this is x n, and I ask you what is x4 minus n, right? If you look at it from and n is going from, remember, we plotted n is going from -10 to 10, right? So -10, -9, etc., 0, 1, 2, 3, 4, up the way and so on. What you're going to do simply to see what that is looking like is to plug in the values of n inside of here and see what values get picked out. So this is in fact either upsampling or downsampling according to this little formula inside of here. So for instance, when n is 4, when n is plus 4, this will be x0, right? So if I look here and let's say this is 0, 1, 2, 3, 4, 5, 6, 7 going on here. When n is 4, right, I am picking out the x0 value, whatever that happened to be in the sequence. If x0 was 0, right, it means if I were to plot that, when n is 4, I'm picking out x0, which is this. When n is 5, I'm picking out x1, which is this one here. Right? So 4, 5. When n is -2, then I'm picking out x6, 4 minus -2. So when n is -2, for instance, here, -2, -1, 0. When n is -2, what I would pick out is x6, which was this one, right? So that is how it goes. So you look at what is inside of here, and whatever the index value tells you, that is the value of the sequence here that you're going to pull out. Make sense? Let me go back to the actual thing here now. So x4 minus n, if I run n from -10 to +10 inside of here, right, it is going to pick out. So for instance, when n is -2, when n is -2, I'm picking out the value of x 4 minus 2, which will be x2, that kind of thing, right? So you could go back inside of there and see exactly what the values are. Yeah? Yeah, no, maybe? So for instance, when n is -4, sorry, when n is 4, when n is 4 inside of here, y4 will be x4 minus 4, which is x0. x0 is 6, right? So when n is 4, we're picking out a value there, which is 6. And so you keep going on. When n is 5, and you can see this sequence actually just flipped and slided around. The next one here, xn minus 3. Well, xn minus 3, you don't even have to, if you remember from your signals and systems, xn minus 3 is just xn delayed by 3 samples. All right, so xn minus 3, xn started here, we delayed by 1, 2, 3. And the whole sequence just slides to the right. x2n minus 3. Again, you index the values inside of there. N is running from -10 to +10. So if you run n inside of here, it's going to sample, if you like, xn by whatever these values from -10 to +10. All right? So for instance, when n is 0, I have x minus 3 inside of here. What is x minus 3? This is the original signal. X minus 3 is nothing, right? We don't have a value for x minus 3 here. So x minus 3 is nothing. So when n is 0, x minus 3 is nothing. When n is 1, we have 2 minus 3, which is x minus 1. You go back up here. Does x minus 1 have a value? No, it doesn't. All right. Then n equal to 2. N equal to 2, that's 2 2s, that's 4 minus 1, so that will be x1. So when n is equal to 1, sorry, when n is equal to 2, we're picking out the value of x1. What is x1? 0, 1. X1 is this value here, which is 5. Right? 5. And so you keep going on, so you'll see what the actual values are inside of there. Yeah? And then the last one is y is equal to x into this thing, n squared minus 2n plus 1. So it's the same thing. These are the index values of xn that are going to be either upsampled or downsampled, depending on the values of n. So if you run n from minus 10 to 10, the actual index values are going to go from 121 all the way up to 81. But the only values that have, the only index values that have any answers are those that are actually going to be between a minus 10 and 10, which is here, right? So x9, 4, 1, 0, 1, 4, and 9. Right? And you go back into your original samples and pick out the values of xn according to those index values. Make sense? This is in fact how you could code things, right? So for instance, if I give you this set of data here, if I give you this set of data and I resample it using a formula like this, and then send that data now, because this is now the data values here, right? So send those data values down the line. If somebody intercepts that, they have no idea what this is what the original data was. But I resampled it using that formula, n squared minus, what was it? N squared minus 2n plus 1. So I resampled it, send the data now, and I alone know to reconstruct it, I have to undo this. So by going back into the data now, I can undo what was sent and reconstruct the original data. But at this point in time, anybody intercepting that data would have no idea what the data is, right? So here's a sort of explanation again inside of here, right? So you could follow it through and see what the actual values and so on, and compare them to your own. I could have made a mistake and it happens, right? Everybody all right with that? Downsampling and upsampling is a huge thing in signal processing, as I said, because it allows us to vary the amount of data we actually have to process. It also allows us to code, and we'll talk about that in one of the applications towards the end of the course that we'll deal with. We also talk about it after we finish our little discussion on the fast Fourier transform, and then we're doing some spectrum analysis. We'll talk about something called zero padding, where you can insert zeros to make your answer appear a little bit better if you're not able. So if I have 10 samples, and I know, for instance, like what we said last week, if I have 10 samples, the fast Fourier transform works better when the samples are multiple of 2 to power of 2. So the closest power of 2 to 10 is, the next one is 16. I don't go down to 8, but I want to go up to 16. So if I have 10 samples and I want to use a fast Fourier transform of it, what I can do is to do something called zero padding, where I add, if I have 10, I add 6 zeros to the end of my data and let the FFT work on that. Now it will be a file of 16 data points, and it will work very well with that. And we will see it gives us a better estimate of the spectrum. But that too is a form of data resampling the data and so on, right? So let me see that. So you would do that to get 2 to the n. Exactly. That is precisely what you do, right? When you have a set of data, if you don't have enough data that is a power of 2, then you add zeros until you get the nearest power of 2. Yeah,